Hello. I'm actually part of an institute called the Molecular Sciences Software Institute. How many people have heard of us before? Actually, like five. That's not bad. Okay. So for everyone else, the MolSSI for short is actually a new type of NSF organization. We're a fully funded institute. So we actually have 36 researchers that we directly pay. So this is staff scientists, this is graduate students and postdocs. And we have about 20 million over 5 years. We do lots of education. So for example, we have actually an education program here in Austin where we'll have actually 60 students in computational liquor science come out for 2 weeks to learn about software best practices and how to make highly performant software. We also do a lot of software infrastructure, which is a little bit what we'll talk about today. And it's kind of this like growing ecosystem and a new way that National Science Foundation is looking at funding various domains. So happy to answer other questions about MolSSI, but we'll probably move to another direction now. All right. So probably another fun question is, what is computational molecular sciences? This is any kind of physics-based simulation, whether this is like quantum chemistry, quantum materials, molecular dynamics, et cetera. So anytime we're looking at molecular interactions with computation rather than experiment, we kind of fall underneath this domain. So a couple things that are kind of popular in this that we really look at and are considered grand challenges within the field. So one is catalysis. So actually, how does an individual molecule interact with some sort of metal center with ligands around it? And these things are very molecular scale complexes. Same thing with like intrinsically disordered proteins, which have a lot of entropy. You can't really make crystals out of them to discover them experimentally. Things like cryo-EM are changing that like a little bit, but it's still hard to get the dynamics back out. And it makes a lot of sense to investigate these computationally instead. So to boil down this field by enormous amount, but for the purpose of this particular conversation, we can really view that what this field does is try to get basically the energy of a molecule. So for example, if I have two molecules, one might be the reactant or product in some sort of chemical reaction. If the energy goes down, that's going to be a very favorable thing. If it goes up, it's going to be much less favorable. So the primary thing that we're after is the energy. We can also get the gradient with respect to nuclear coordinates. So how does a molecule change over time, or what is perhaps a more optimal configuration for the molecule? Higher order derivatives as well, such as Hessians, are quite popular, where the Hessian will actually give you IR spectra. So you can actually rebuild up what the infrared spectra of an individual molecule is, so you can kind of experimentally determine what it is. So all these things are really quite interlinked. So then the really fun thing about quantum chemistry is that this field has been around for a very long time, about 50 years. And so we actually know how to solve effectively the Schrodinger equation exactly, which will give us the energy in a virtually exact way. The primary issue with this, however, it's an NP-hard problem. It's an n-body problem, which is virtually intractable to solve exactly. You can do fun things like water, like a single water molecule, which is interesting but not really very extensible. So to go to much larger systems, like all NP-hard problems, you start applying heuristics, you start applying approximations. So from that, you get lots of different methods that scale in various different ways. So usually lower bound for quantum chemistry is about n cubed, while upper bound is about n to the 8th for fairly practical and routine methods with respect to number of nuclear coordinates. So these things still scale really quite horribly. And then the other fun thing is, due to the number of approximations involved, you can have hundreds or thousands of different methods that researchers all across the globe have been building for 50 years, and then you kind of build up this effective zoo of different methodologies that make all kinds of different approximations. They'll have all kinds of different performance metrics and accuracy metrics, and some work in different chemical domains than others. And on top of that, you end up with a lot of different programs. A lot of these programs are able to compute very similar methods, but some programs have very specific methods that only they possess. These programs have been around from anywhere to 5 and 50 years, consist of 100,000 lines to 5 million lines of code. So they're extremely enormous programs that actually kind of run this in the background. One final thing about quantum chemistry that I really like: input-output is on the order of kilobytes. Intermediate sizes may be terabytes or more, and computational costs may be quite insane. I think one of the really fun things that we get on issues a lot is like, hey, I tried to do a calculation that if you do an envelope sort of thing, that it's going to like request like basically total energy output of the sun to compute. And it's like, you can't do that. So it's hard to tell, especially with these MVA methods. Like they're just complete walls, and understanding how much that scales is very difficult for most people.
Okay. So for the most part, these are executables, and they've been built up for a long time and in many different languages, and also their parsing is in those languages like C++ or Fortran. And so these are some representative input files that are nominally running the same method in 4 different programs. Here's 2 that are pure ASCII, and here's a couple newer ones that have Python interfaces. Nominally, these are the same, and so this red should be running the same thing. But you see there are several different spellings, and sometimes you need to know extra things in order to even run it. And so there's a great deal of wasted scientific brain power in remembering all these different spellings and names and character limits. Sometimes, as you see in the purple, you can access the results, and sometimes you can't. You just have to parse the ASCII. So there's a great deal of overlap. Many programs compute the same things, but there's also fragmentation. Certain methods can only be computed by one of those 20 programs on the previous slide. So what do these look like on the inside? This is not an exaggeration. These are highly coupled things. Even the core developers don't know all the nooks and crannies, because it could have been that a grad student programmed up this bit for one particular paper, left, and no one's ever looked at it again. And if you look at it closer, you can see homespun versions of things that you might recognize as serving the role of BLOS or MPI, or parsing, or even a tensor class. So you might wonder why we don't just ditch these entirely. And that is because scientific reproducibility sort of relies on this, because in the middle are all of the good theses and journal articles and the ways to compute papers that have been programmed up by the one person who understands how to do this and who has optimized and debugged this code over the past decades. But all the same, this is unwieldy and doesn't fit nicely into the Python ecosystem. What we end up having to do is just call subprocess on these executables. So we'd like to have an interface between these so that we can behave more like other domain-specific Python things like SciPy or AstroPy. So some things to keep in mind is that we don't want to be strongly coupled like within these quantum chemistry programs. We want loose coupling between any modules that we develop. And we don't want this low cohesion Swiss Army knife type thing where this is sort of a vertical monopoly. Instead, we want several small modules with high cohesion that are reusable and understandable and that do one thing and do it well.
So in order to help with this modularity, one of the ideas here is we need some sort of abstraction layer or common representation that all these programs can pass through. So of course, whenever you start saying this, which you're really coming up with the schema. So schemas are very, very hard to do. The XKCD comic really applies. There's definitely a lot of prior art there. We're trying this one more time, kind of like as MolSSI is this large institute, we hope that we have like enough reach and longevity to actually build out a community schema. We start this with lots of ideas actually found at the SciPy conference of how to build communities. You take all these things, you mix them together to main science, you hold lots of conferences, you hold lots of conversation. I could probably spend an entire conversation about how to actually try to build a community-wide schema. The big thing is it's not trivial in any respect. I think one of the interesting things that we found is for about the first year of a schema, like people would quibble over like, is this plural or is it singular, or is there an underscore here or something like that. And eventually I think people effectively got bored of that. Like they kind of stopped realizing that like, like the small things kind of can get washed under the rug. It doesn't really matter. I just have some sort of key. And so we've been in really this kind of like decision stage for the past half year, and then we're finally in this implementation stage, which has really only come out recently. So I just wanted to mention that, difficult, but definitely workable. The other thing is in quantum chemistry, we kind of want like this nested object schema. And so what I mean by that is like I might have something that represents a quantum chemistry molecule. So that quantum chemistry molecule will be part of a quantum chemistry input. So I can kind of build these things up modularly. Of course, if I want any kind of reproducibility, my input is going to be part of my output. So these things kind of walk along. So in my output, I have everything in my input. And so in this fashion, I can build up something that will do a single quantum chemistry computation. Again, what we're really after is kind of like this loose coupling, this decomposability. So if I can then refactor all of my individual inputs into something like a geometry optimization, I can go ahead and successively build up this hierarchical object-based model using these schemas. I think one of the big reasons that we can get away with this is because our data is really quite small. If you have much, much larger data, like you see in other fields, like this kind of approach breaks down really quite rapidly. And then finally is like, we actually have methods that require, many thousands of geometry optimizations. And so like these kind of things you can sit above this, and we kind of have these large hierarchies of schema results. So now that you have a schema, the first thing you need to do is actually start implementing a schema. So we've done this with a Python 3.6 plus library called Pydantic. I really like it because what it does is it allows you to build out classes that have validation upon them. So for example, if this schema version was not an integer, if it was a string, it could either type coerce it if it could from a string of 1, or if it was like a string that couldn't be type coerced, it would throw an error saying that that's invalid schema. The other nice thing about Pydantic is you can do these hierarchical models. So for example, like in here, that molecule and model is another Pydantic objects. And so you can do kind of like this recursive validation all the way down. And the other really good thing about it is you have all the serialization. So one of the things that we want to do is start like going to transferring data over the internet, transferring data between programs. You think about like how can I take these models and automatically put them into JSON or message pack. And so this can happen automatically with this kind of Pydantic tab. And so you have like this recursive model building up and down. The other nice thing is you can serialize this not only to JSON, but something like message pack if you have arrays and you want a bit more performance. All this is kind of, not everything is built in, but it's all doable through this kind of Pydantic model. The other thing that we can do is now that we have not just schema, but let's add visualization to it. So if I want to have like a Jupyter notebook, of course, I want to visualize molecules, and then if I have this kind of tech, I can build up things, so build up even further. So if I have like my an optimization object, I can say like, what's the, show me like how my energy converges as a function of iterations and things like this. So I can build in a lot of visualization onto these objects themselves as well. Oops. And this one's me too. So then once you have the schema implemented, you need something that actually can compute these things. So this has been done before in various ways, but what we really wanted was something that not only would parse input and output, but would actually evaluate these models too. It would be able to handle OMP, MPI, parallelization, etc., and provide like a model that you just say, give us the input, give it these resources, and just like let it go, and you get one of these result outputs back. So in this kind of fashion, we're actually able to start abstracting away all these individual programs because we're running them all through the schema. So I put a schema in, I just say like, I want to run program A. It can go off and evaluate it if program A exists. If it doesn't exist, it'll throw an error. And so in this fashion, like it's like the first level of like this kind of composable and buildable ecosystem. So for example here, typically geometry optimizers, like nuclear geometry optimizers, are baked into these programs. So that means that program A has its own geometry optimizer, and you can't use it with anything else. So for example, if you need some sort of method from program B, you can't do it because that optimizer is baked in. Latest generation geometry optimizers are built in Python ecosystems typically, and from this they're able to use tools like QC Engine to actually run any of them in the background. So in this particular case, we have a JSON input. What I really like about Pydantic is JSON or JSON-like objects is equivalent to an object. So it's kind of Java-like. I pass this in, it's coerced to an actual object, and then my output's going to be an object where I can look at like what's the coordinates of my final molecule. And so then I can switch out different programs by just switching out 2 lines of the code. Very similar, I just say what program, what method, and then you can see my results will vary slightly because of the different approximations involved. And I can keep on doing this, and we're up to about a dozen projects so far. And what I really like about this approach too is it doesn't only cover quantum mechanics. We're plugging in molecular mechanics backends, semi-empirical backends, all the new machine learning-based energy and gradient evaluators. We can plug this into so that every single code above this is able to make advances of all these tools that are evolving. So it becomes, again, a very, very composable software ecosystem.
So with SCHEMA, and a SCHEMA runner in hand, we can start extending the capabilities of the types of calculations that we do. So first we'll look at this composable driver. If you want a Python API for quantum chemistry, you want to be able to run an energy, gradient, or Hessian. And in the simplest case, someone has already computed the analytic forms for this in your quantum chemistry engine. And so in this case, the driver would simply return the input JSON for that calculation. But there are more complicated methods where, say, you take a molecular cluster and break that into fragments, in which case is going to return an input for each fragment. Or you use a couple methods in order to better approximate an energy, so it's going to return several input files again. Or you want to do a finite difference derivative, so it's going to return a displaced input files. So any one of these could be the path that gets called when you do an energy gradient or Hessian. And these are completely composable. You end up with a pool of QC JSON schema. And then this is passed into QC engine, which in turn calls a compute engine, in this case, the quantum chemistry program Sci4. And this is shown continuous, but you can also do it in parallel. And then with the pool of results, these pass through assembly stages in order to get out your energy gradient or Hessian final answer. So for an example, you can see what the task graph of this looks like. This is an optimization of a water dimer where it's broken into different fragments, and then different methods are run on each of the fragments, and then these come together in order to form a gradient, which gets passed on to an optimizer, and then it repeats until the optimization converges. So this is starting to look more like the Python ecosystem that you're familiar with.
So we're kind of going through and showing like all the different pieces of technology that we can really invent like once this base layer is in place. So another one that we hear a lot is, between, well, I guess a better way to say this is probably 10, 20 years ago, like running 10 quantum chemistry computations would result in about a paper, so you didn't really have a data management or execution problem. Today, that's more like on the order of 10,000 because quantum chemistry is very static. You need more kind of like ensemble approaches to really get at the science that you're interested in. And on top of this, you have machine learning approaches, which are going to be running tens of millions of computations, and being able to orchestrate that and organize that is going to be really quite crucial. So the Quantum Chemistry Archive is basically both hybrid compute orchestration and data management all in one. What's nice about this is you can run it on a laptop, or you can really run it at scale on hundreds of thousands of cores simultaneously. So it's as elastic as you have compute time for. What's also nice about this is because we have these serializable representations, we have internal databases, which means that we can have Vue clients and Jupyter notebooks where people can pull data from a central server locally. The database may be terabytes, but you can only get like a very small slice of that. So building out these query layers is quite straightforward with kind of like latest gen hardware. Another thing is you get lots of ease of use, so you don't have to basically write a Python script which writes a domain-specific input and then something that will run it and then something will parse it. All that's kind of taken care of for you. So it kind of moves the needle a little bit so that you need less experts to actually run the software. And then finally, this is kind of quite new, is everything is actually installable via Conda. And so what really makes Conda different is like before you'd have to like sign some sort of contract with someone and they send you a binary file that you could potentially run on your computer. So we're trying to kind of switch that up and actually run all of our high performance code through Conda, which I can talk a little bit more about later. So Another thing is once you have the central database, you can kind of think about like, I need multi-physical site compute. So what this means is, say I'm a PI, I might be running on my local campus cluster, then I get an XT grant. How do I shift tasks between these two things? All this can happen automatically if I have basically managers which take pieces of a global queue, ship them to a local resource. These local resources will use some sort of task distribution manager. Probably the most known at SciPy is Dask. Dask has Dask job queue, which can do this. But depending on the scale, you probably want to use something like Radical or Parcel to scale up to hundreds of thousands of concurrent cores. And what's really great about this tech is we're not really bounded by any kind of compute. Handling, we ran on Theta using everything kind of installable. We scaled up to about 100,000 cores. Concurrently, absolutely no issues on performance, hit like 95% efficiency. So these kind of approaches for embarrassing parallel computations work extraordinarily well. And so this really allows kind of like this elastic nature from single laptop all the way up to multiple physical sites. Another thing is you see a lot of projects like this in other domains. So for example, in the materials, you have centralized databases, but you can't really spin up the server yourself. So you can't really have private versus public data. So for us, everything is open source. So you can spin up the server and have private data if you want to prepare something before a paper, and you don't really want it to be public until that paper is published. That's great. You can push it to a Slater if you want. So the central MolSSI server is kind of like community data. We really focus on fair data standards. So currently, in just a couple months, we did about 3 million computations, covering about 700,000 core hours to kind of give you an idea of like what the scale of this is. And so normally, like a typical paper is like on the order of tens or 20th thousands computations. So moving the needle by multiple orders of magnitude. And as mentioned, we actually have a free client. You can just go on, download, start exploring our data. Through Jupyter Notebooks, you can look at statistics, analytics, do all kinds of fun visualization, look at molecules, all in like this kind of like interactive setting, using like best-in-class like Jupyter visualization tools and like the apply to this ecosystem.
Okay. So even with QCJSON schema and parallelism, you're not home free because all of these input files, because they run through different programs which have different defaults or maybe slightly different implementations of a method, they will not give you exactly the same energy for what looks like exactly the same calculation. So QCDB, the common driver, is a light wrapper on top of all of this previously mentioned tech that evens out the input files and imposes the best practice options in order for calculations to run fastest, and a single name for a lot of these options, so that something like this would be the same in 4 programs, and you're only specifying the names of the programs in order to go between these. And this helps substantially to lower the barriers to using a variety of codes, so that you can get the best, so that you can use the best code for your particular problem at hand. It also evens up the output somewhat by more carefully defining some output quantities and imposing some known relations that ought to be true. And this helps substantially in terms of database searching within QCFractal. So what does this ecosystem look like? This is an approximate current representation. You go from upstream, where out here in light blue are the basic Python tools, Python, NumPy, et cetera, and the basic non-Python tools, BLOS and PyBind 11 and such, all the way through to quantum chemistry programs and to downstream. These are community domain-specific libraries that do a particular thing, like solvation or dispersion. And these add on additional capabilities into a quantum chemistry program like Sci4. And then Sci4 used to have interfaces that have since moved to QC Engine. And so these help drive some other add-on programs with additional capability. And so Sci4 now calls QC Engine directly, as well as being an engine for quantum chemistry from QC Engine. From QC Engine, this is what actually does the quantum chemistry for QC Fractal, which does the database and storing and job queuing. And then QCDB is the outer wrapper on that. So this represents a progression over the past few years from taking community libraries and embedding them within the Sci4 repository to moving towards independent libraries with API calls. And then for packages that are called infrequently, we can actually narrow that connection further to using JSON. And now we can move towards the community schema and call these indirectly through QC Engine so that these libraries can be further more widely used within the community. So for research and development purposes, we're mostly interested in the output of Sci4 or QC Fractal or QCDB. But because of all these additional capabilities that we've decoupled from these main projects, we actually end up maintaining all of these ovals. And then because binary packaging is not big in the quantum chemistry community, what we actually end up packaging through Conda and CondaForge are all of these ovals. And another important thing is to actually give back to the parent and non-chemistry projects, which we've done a few of and a few more that couldn't fit onto the slide.
So the short conclusion is kind of if we think about these really large packages and we think about like what's the lowest common denominator, and if we can have abstraction layers within the Python ecosystem, what are all the things that we can build on top of that? So like we're seeing like kind of like this sort of explosion in terms of modularity and interoperability within the domain that's kind of enabled by these sorts of tools and ideas. And you know, I think a lot of people doubted that like you could actually manage all this due to the complexity and the number of packages involved. But via things like CMake and CondaForge and other Conda channels, we're actually able to run tons and tons of compiled code and highly performant code through these canonical package managers within this ecosystem, attach them to Python in ways that like I think would be previously just simply unmanageable. So we have, you know, 50, 60 dependent packages in a network, and it all actually works together really quite well. And this kind of encouraged us in the future to build even more interoperable packages where instead of like building one more monolith, we have lots of individual packages, which honestly does complicate our life a little bit. But at the same time, we're kind of seeing like an inverse pyramid of adoption. So something like Elemental, which is the implementation of schema, has a lot larger adoption than Engine, which is the execution layer of that schema, which then Fractal has less of an adoption because it's, you know, an even higher level outer shell for these sorts of things. So this is something we really like to see because we can kind of build out an ecosystem based off these very, very low level packages. And so with that, this is the work of just a ton of people, a ton of organizations and funding agencies. So this is just a fraction of them up here. And so we really want to thank the community that's helped us build these kinds of tools as well. Thank you.
Just a couple of questions.
Sure.
This is nice. So I'm an old friend of Robert Harrison.
Ah, great.
Yeah. I like the way you're doing this. There's two pieces that I'm worried about. You've totally excluded commercial software from the schema outside Terracam. But anybody else there's no other engines I see that you're talking to get that schema involved.
So actually, codes like MolPro are picking it up, as well as the various Dalton packages. You know, QChem will as well. Something like Gaussian might be a little bit more stubborn. So it's just simply the fact that we have a lot easier access to them. They've always been involved with the creation of the schema, so we're not excluding them in any fashion.
Okay. And the other question is, as you're going to high-performance computing where you can't use Dask, where you have actual other schedules like PBS, Pro, how do you manage that?
Sure. So the various task execution layers, such as dash job queue, parcel, etc., actually interface with all those schedulers for you. So what they do is they're based off a 4-layer ecosystem where effectively what they do is they wrap all the different schedulers. They put a worker on one node or many nodes, and then they have an internal queue that ships those tasks out to it. So yeah, we actually run exclusively on campus compute behind PBS and Slurm, and they also hook into something like Kubernetes, so we've actually tried it out in AWS as well without any issue.
So I really enjoyed the talk. I just have a question about the database. So say somebody wants to run a computation that's already been run before, like, is there a way to look that up, or do you already automatically check the database for something similar that's been run?
Absolutely. So with the database and everything serialized, we know exactly what computations have and haven't been run before. So if you try to rerun a computation, you just immediately get the result instead of rerunning it. Mm-hmm.
We have time for one more.
I mean, I'm kind of new to the Python community, but I'm really encouraged by what looks like a community model and how you've really tried to rework it in a way that is going to take out a lot of the quirks and nuances that only one person understands. We have a similar problem with where I work at NCAR. We have weather models and climate models that are very, very similar. There's thousands of people that have each contributed a little piece of the physics or something. If you ever thought about trying to describe your process to help other communities, it might be really great. Maybe other people have tried to do that already. I don't know, but I think it'd be really valuable.
Yeah, so we actually have a couple papers planned trying to describe this ecosystem. So from like technical details like task distribution on supercomputers all the way up to like the general modular structure. If you give me your card, I'd be happy to send them to you as they come out.